So today we start with higher order differential equations by laying out some foundations. We're not exactly going to be solving for anything today yet, because we need to lay out some foundation. And for us, our focus will be on linear differential equations. So let's start talking about nth order linear differential equations with initial conditions. So an initial value problem, an nth order initial value problem for a linear differential equation would look something like this, where we would have a function of x times the nth derivative of y with respect to x plus another function, and then we start counting the derivatives downward. And then we would include the function that we're looking for, the dependent variable y. And remember that to make it linear, we have to get the function y and its derivatives to not be composed with any other functions like the square root or sine or anything like that. That's what makes it linear. But we're allowed to have functions of x, like square root of x or the ln of x or x to the third power or whatever. Now, the initial conditions, before we only had one initial condition for our first order differential equation. If you have a second order differential equation, you should expect two initial conditions. In third order differential equation, you should expect three initial conditions. So for an nth order differential equation, we should expect n initial conditions. So that completes your initial value problem. You have a differential equation, and then you have n initial values. Okay? Now, if you have this scenario where you have your linear nth order differential equation, and you have n initial conditions, and the initial conditions has to be, this should be an x squared. It's not here. Your initial conditions need to center on one particular x naught value, and it gives you values for the original function, the first derivative, second derivative, all the way up to the n minus first derivative. So if those are your initial conditions, and then you have this differential equation, then you're guaranteed that a solution will exist, and that solution will be the only solution. Existence and uniqueness theorem says that you're guaranteed a solution, at least some function that is, or that contains x naught. It might not go from minus infinity to positive infinity, but at least it should contain x naught, because that's where the initial condition happens. Okay, so that's the theoretical part of this. So here's an example where we have a second order differential equation. Your differential equation is y double prime minus y is equal to 0. And then you would have two initial conditions. Initial condition at 0, where you have the value of y at 0, and you have the value of y prime at 0. So those are the two that we need. So this is your differential equation and your initial condition. So this is your IVP. And in this particular problem, just kind of like as a warm-up, they want us to check to see if we can find a unique solution in this y equals c1 e to the x plus c2 e to the negative x. So they're saying that this is a solution, and we want to find a value for c1 and c2 that would make this fit. Okay? So let's see if we can find it. First of all, you should probably check to make sure that this is actually, in fact, a solution. And we could do that by just taking a couple of derivatives and seeing what happens. So let's do that as a first check. For this particular problem, we want to find a particular solution that would fit this initial value problem. And so that would fit these two initial conditions. And so they're giving us the answer already, which later on we'll actually find ourselves. But for now, they're giving us the answer. And then this is a two-parameter family of a solution, because there's a C1 and C2 that we don't know. And so essentially, we have to find C1 and C2. Well, we have to use both initial conditions at the same time to find C1 and C2. And we have to find C1 and C2 at the same time. It's more together. We're finding it together. So it's not like one first and then the other. We're actually going to try to solve for C1 and C2 at the same time. Yeah. But before we do that, I want to make sure that this is in fact a solution. And so what we're going to do is we're going to do a check just to see that this works. And it looks like we need y double prime and y. So let's find y double prime. So this is our first check that y is a solution. We need y double prime, so we need y prime first. And so our function y is this c1 e to the x plus c2 e to the negative x. So we need to take the derivative of that with respect to x. So c1 is a constant, c1 e to the x, the derivative of that is e to the x. Derivative e to the negative x is negative e to the negative x. So there's a minus sign. So that's the first derivative. And then the second derivative is the derivative of the first. And then let's just drop it into the solution that or into the differential equation. So our differential equation is y double prime minus y is equal to 0. So y double prime we found out to be c1 e to the x plus c2 e to the negative x. And y is the same thing. And that is 0, so that checks out. So let's just be clear on what we just did here. We got y double prime minus y is equal to 0. So we can say, okay, that worked. That's good. And now let's actually answer the question, which is to find that unique solution, or to find C1 and C2 that would make this work. Mario? Carlos? Say it again. It would be negative, but we got it from the y prime. So it's a negative and a negative, and then that would make it positive. Right? Yeah. All right, so that's done. Now let's actually find the solution. Let's actually use the initial condition. to solve initial conditions. There's two of them, right? So that's to solve for C1 and C2. And so y of 0, we have y, right? I can't see it anymore. We have y right here. This is your y. Y of 0 is putting the 0 in for the x's. And y of 0 is supposed to equal to 0. So that's one equation with two unknowns, and then we'll use a second initial condition, the y prime. So y prime of 0, y prime, we did y prime over here. So that's C1 e to the 0 minus C2 e to the negative 0. So that's C1 minus C2 is equal to 1. And it looks like we have something that we should be able to solve for by just looking at the second initial condition. And the first initial condition was from. So we'll add it. I think this is 2, C1 is equal to 1. So C1 is equal to 1/2. And then C2 should equal to negative 1/2 maybe. So our actual unique solution is going to be the same function essentially, except we know what C1 and C2 are. So C1 is 1/2 e to the x plus C2, let's just say negative 1/2 e to the negative x. Okay, that's it. So this is our unique solution that exists for this particular initial value problem. Say it again. Well, this is like the later half of what we need to do eventually. Eventually, we'll actually figure out how to find our general solution. This is our general solution. Eventually, we'll learn how to find that. And then if we have initial conditions, then we still would have to solve for those arbitrary constants. Okay? So we're just, again, laying down a foundation. And so we're getting a little warm up on some linear algebra, because we're going to just dive into some linear algebra here pretty deeply. How many people have taken linear algebra or are currently taking it? How many people have not taken linear algebra? All right. Well, we don't need that much linear algebra. It's just for those people that are currently taking it now, there's some aspects of this that's going to be really important. All right. Let's move on to another type of problem that's not going to guarantee that you're going to get a unique solution, and that is a boundary value problem. So a boundary value problem is you got a differential equation just like last time, except your conditions are not initial conditions, which means that you don't start off at a particular point. Your conditions are conditions about the boundary. So as an example, we'll take a look at a second order differential equation. We're going to stick with linear differential equations in this chapter. So we have a second order differential equation, and then instead of having y of a is equal to something and y prime of a is equal to something, you have an a and a b as an input for your boundaries. So they give you some information at some points between a and b. Now the information they give you might be a couple of points in a and b. It might be slope in a and then a point on b, or whatever. Okay, so there's two conditions that we need for this second order differential equation, and the condition can either be it's going to be, first of all, it's going to be at the boundaries, and then at each of those boundaries it could be a point or it could be the slope at those boundaries. And so you'll have four combinations for a second order differential equation. You might have information about the points, or you might have information about derivatives, or you might have a combination. So so in this particular scenario, there's no guarantee that you're going to get a solution. And I think for now, that's all I really want to say about this, because we're not going to do too many boundary problems. And so let's move on after this. You can read more about it if you want. But I had an example that I was gonna do, but I want to make sure we get through the rest of this section first. And this section is actually 3 parts, so we got some stuff to do. Yeah, I guess it would be, what do they call it? This is chapter 4, section 1, so this is 4.1.1. So 4.1.2, the second portion of the section, talks about a particular kind of differential equation called homogeneous. Now, I think we define homogeneous by multiplying times, substituting t times x and t times y or something like that. So that was an unfortunate use of the word homogeneous, because homogeneous in most other cases means that something is equal to 0. And when you abbreviate homogeneous, like I've seen in some of your test responses, try to use hom. When you abbreviate homogeneous, try to use HOM instead of HOMO. So we have a homogeneous differential equation is to say that your linear differential equation on the left-hand side is set equal to 0. A non-homogeneous differential equation is essentially the same thing, except instead of equal to 0, it's equal to g of x. So again, if you've taken linear algebra, there's some glimpses of this in linear algebra when we studied homogeneous and non-homogeneous systems of linear equations. So now the thing about this, or the theory behind introducing these types of differential equations, is that in order to solve for the non-homogeneous system, you actually need information about the homogeneous differential equation first. I said system. Let me say that again. In order for you to solve for the non-homogeneous differential equation, you need information about the homogeneous differential equation first. So in solving for this system over here where you have this linear differential equation equal to g of x, you actually have to solve for that same system where it's first equal to 0. And we'll talk about how that builds on itself when we start finding solutions. Okay. So what's this? Just examples? So just in terms of classifying, let's talk about these examples over here. The first one is what order? This is a third order. This is linear because the y's are not taken to any weird composition with any other functions. Third order linear, non-homogeneous. And then our other example down here looks like it's a fourth order, right? Also linear, but this one is homogeneous. Do we know how to solve for this? No, we don't know how to solve for this yet. All right, so let's figure out some of the solutions or how the solutions might look like when we're dealing with these types of differential equations. Let's skip over the differential operator. Linear operator. We're going to go into the theorem called the superposition principle. Yeah. All right. So there's this thing called the superposition principle. And this says that if y1, y2, all the way up to some number of y's are solutions to the homogeneous differential equation, then the function c1 times y1 plus c2 times y2 plus dot, 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 and all that is also a solution to the differential equation. So the superposition principle tells us that we can just string up these solutions in this way, and then that whole thing together is also a solution. Now that's kind of interesting. Anyways, do you guys know another name for this idea of stringing up all these functions together like this? Maybe somebody who's taken linear algebra or is taking linear algebra. A linear combination. Linear combination of the functions. So in linear algebra, we tend to look at vectors. So we say linear combination of these vectors. Here, these are functions. So we could say that it's a linear combination of these functions. But did you know the functions can also be seen as vectors? Yeah. We can go into a little bit of a tangent on this, maybe maybe later. So this idea of having a constant times a function plus another constant times another function, etc., is called a linear combination. So let's take a look at this function right here. Let me see if I can come up with an equation that would make this true. E to the x. Would e to the x work for this? Would e to the x work for this? Yeah? Actually, there's an actual example. Maybe I should just stick with that. When I try to come up with my own examples, they tend to go bad. Here's one. So they say that e to the negative 3x and e to the 4x is a solution for this differential equation. Okay, let's just trust that that's correct, that it's true. And so let's actually show that y equals c1 e to the minus 3x plus c2 e to the 4x is also a solution. Okay? So what do we need? It looks like we're going to need the first derivative and the second derivative of these things. This particular function right here. So let's find the first and second derivatives. Y prime is equal to, there's going to be a negative 3 that comes out. And then the derivative of this term would be, there's a 4 that comes out. So the second derivative, negative 3 comes out again. Negative 3 times negative 3 is positive 9. And then 16c2 e to the 4x. Okay, let's drop the y double prime in for y double prime in our differential equation. 9c1 e to the minus 3x plus 16c2 e to the 4x. Now we also found the first derivative that we'll need to use for y prime. That's a minus 3c1 e to the minus 3x plus 4c2 e to the 4x. And then y was this linear combination of these two functions. It's c1 e to the minus 3x plus c2 e to the 4x. And this hopefully will equal to 0. This is to prove that the linear combination of these two functions here is also a solution. Yeah. A linear combination means you take one of these vectors, or we'll take this function and multiply it by a constant. And then you take another one of these functions and multiply it by another constant. And then you add them together. That's what a linear combination means. So if I have y1, y2, all the way up to yk, a linear combination would be constant times y1 plus another constant times y2 plus all the way up to the last constant times yk. E to the negative 3x and e to the 4x. So those are your y1 and y2. And a linear combination would just be multiplying it by a constant and then adding them together. No, we're not looking for C1 and C2 in this particular problem. All we're going to say is that if we use this as your y, then it should satisfy this differential equation. So this is like a check to make sure that this is a solution. Each of them is a solution. So if I went and did this and put that into this differential equation, I'm going to get 0. We're not doing that, but we're just going to assume that because I got this from the book, and that's what they're assuming. And now what we're saying is that if we put them as a linear combination, then that's also going to work. And by work means it's going to work if we find the first and second derivatives and we put in the first and second derivatives, and then this is going to be a true equation, hopefully. All right, what do we have here? We have, I'm going to underline, looks like they're going to be like terms here. There is a bunch of terms that has C1 e to the negative 3. So what terms do we have there? We have a 9, we have a minus negative 3, we have a minus 12. C1 e to the minus 3x. So I'm just collecting the coefficients, and that's those like terms. Now I'm going to find the other like terms. The other like terms are C2 e to the 4x. And so what's the coefficients for that? We have a 16, we have a negative 4, and we have a negative 12. And each of these coefficients will turn out to be 0. So that does work out. And so this is just a check to make sure that the linear combination of the functions of the solutions are actually is actually also a solution, given that we already have these solutions. Now we still don't know how to find these solutions, which is something that we'll do next time. But right now, all we're showing is that if we have two solutions, then we can just add them together and then multiply them by a constant and add them together, and then we would still get a solution. And what we're doing is we're trying to find the most general solution to these differential equations. Okay? That's what the superposition principle says. Superposition principle says that if you have one, or if you have two or three solutions, you can just multiply them by constants and add them all together, and that's still going to be a solution. And the key is going to be, we want as many of these little solutions as possible that would match the order. So if we have a fourth order differential equation, we should be looking for 4 little solutions. Little solutions. What does little solution mean? I don't know. Let's figure that out. Okay? Is this good for now? I don't know if I want to do the example, but A corollary is something that follows a theorem that doesn't need much proving. A theorem needs a lot of proving, and we're not proving the theorems here. It's not a real math class. But a theorem is something that you normally would, it's a big statement, and then you would prove it. A corollary would come after a theorem that follows from the theorem, and there's not much work to do. So here, there's a couple of corollaries. It says that if y1 is a solution, then a constant times y1 is also a solution. That seems to follow naturally, right? And then the trivial solution, y is equal to 0, is always a solution to a homogeneous differential equation. Because if y was equal to 0, then the derivatives of y are all equal to 0, and then 0 is equal to a homogeneous differential equation is equal to 0, so that's all going to work out. I don't think we need to do this. Let's just take that out. All right, so these are a couple of corollaries that come after a homogeneous differential equation. Now, what's the deal with those functions? So we're finding these functions, or they're giving us these functions. And I said that you should have as many of these little functions as possible. Now, what do I mean by little functions? The functions that we're talking about have to satisfy the collection of functions that we need to find have to satisfy a particular criteria, and that it has to be linearly independent. So more linear algebra flashbacks or foreshadowing, or remember what we did a couple of weeks ago in linear algebra. If you have a set of functions f1, f2, all the way to fn, then they are said to be linearly dependent if you can write them as a linear combination of each other. Linear combination, remember, is constant times a function plus a constant times a function plus constant times a function, all the way until you finish all the functions. If you can write them as a linear combination of each other, set them equal to 0, and then you can find at least one value of c that's not equal to 0. Now, if the only way this thing would equal to 0 is that if each of the C1, C2, C3, all the way up Cn are all equal to 0, then it's called linearly independent. That's usually how it's defined first before it's the dependent. It's usually independent first, but for some reason they did dependent first. No. Well, I think the idea of free variables would be a little bit different to deal with here, because we're not, in this particular definition, we're not dealing with matrices. Okay. So a quick example is that if your f1, let's use y's. I don't know why they switched to f. If you have these three functions, you want to know if they're linearly independent or if they're linearly dependent, then you can write down this equation, a linear combination c1 e to the x plus c2 times x plus c3 times 4x minus e to the x and set that equal to 0 and ask yourself, can you find a value for C1 and C2 and C3 that's not all equal to 0? Now, if C1 and C2 and C3 are all equal to 0, then that's going to be equal to 0, right? That's not a big deal. So the thing is that if you can find at least one non-zero value for either C1, C2, or C3, or a combination of them, then this set would be dependent. Does that make sense? It would be dependent. If you can find a non-zero value for C1, C2, or C3, I mean, one of them can be 0, but then if the others are non-zero, then you found something. So it would be dependent. Yeah, it would be dependent. So can we? What? This would be what? 1. And the C3 would be, what would C3 be? 1. So C1 equal to 1, C2 equal to 4, what? Negative 4. So our conclusion here, we found C1, C2, and C3 that's not all equal to 0. So our conclusion here is that Y1, Y2, and Y3 are linearly dependent. Okay? And just as a contrast, let's do an example quickly where y1 is equal to e to the x and y2 is equal to e to the negative x. Just two functions. Now, can I actually find a value for c1 and c2 so that this linear combination equal to 0 would get me a value for that to equal to 0? So in this particular case, the only way to get 0 is if C1 and C2 are both equal to 0. And so if that's the case, what do we say about y1 and y2? Y1 and y2 are independent. So our key is to look for functions that are linearly independent, and then we're going to string them up. Because if they're dependent, then the whole idea of a linear combination will just kind of, we're just going to be repeating a bunch of functions. So we want to count as many independent, linearly independent functions as the order of your differential equation, because that's how we're going to find the solutions to these differential equations. Okay. Now, finding out whether a set of functions is linearly independent or dependent using this method is not the easiest thing to do, especially if you have a lot of them. And so it turns out that there's another way to find linear independence for these functions. And that is the Wronskian. So, more linear algebra. Suppose you have functions f1 through fn, and we have to include a condition that they have to have appropriate derivatives because we need to make these derivatives. The Wronskian is going to be a row of functions and a row of first derivatives, OG function, first derivatives, second derivatives, etc., to the n minus first derivatives. So that makes a square matrix if we put them in a matrix form. And so the Wronskian is defined to be the determinant of that matrix. And for us, we're just going to be dealing with 2x2 matrices and maybe a 3x3 matrix so that we can figure out how to find the determinant of that. But finding the determinant of these matrices requires either some linear algebra or I'll just tell you the formula. And then we'll find the formula for a 2x2 matrix, and then for a 3x3, it's going to be a little bit of a method. So the Wronskian is the determinant of this square matrix of functions. And it turns out that if the Wronskian is not equal to 0, then you have yourself a list of linearly independent functions. Okay? So we had two examples. We had one example where we had two functions that are linearly independent. We had another example where we had three functions that are linearly dependent. So let's try to find the determinant of those. First, let's find determinants. So let's go on a little tangent to talk about determinants. And if you've taken linear algebra, you know all this already, then I don't know, whatever. 2x2. If you have a 2x2 matrix that has elements in 4 different slots, then the determinant of this, first of all, the determinant is usually denoted by just a vertical line instead of like brackets or parentheses for matrices. If you see a matrix that has vertical lines or absolute value, they're essentially looking for the determinant. So the determinant of this is going to be A times D minus C times B, or B times C, it doesn't matter. So that's it. That's easy. The determinant of a matrix, a 2x2 matrix, is the product of the diagonals minus the product of the other ones. Now, for a 3x3, we have to expand so what we need to do is we need to expand on either any row or any column. And so here's an example of expanding on a row. Expanding on a row, it's going to be, let's actually say that we're expanding on a row. So we're going across the row. It's going to be the first number here, A, times the determinant of the 2 by 2 matrix after you cross out the row and column that contains A. So I cross out the row and column that contains A, and I have a small subset left, E, F, H, I. And so that's the determinant of that 2 by 2 matrix, which you can find. Now, it alternates to go from plus, minus, plus, minus. So we start off with A being a positive, and then now we go to B, which is a negative, and there's a negative sign here, and that's negative B. Now cross out the row and column that contains B, and what are you going to have left? You have DF and GI. If you cross out the row and the column that contains B, that's what you have left. And then we're going to go to the last, expanding on the row, we're going A, B, C here. And then the last element here is a plus, positive C. And then cross out the row and column that contains C, you have D, E, G, H. Okay. Now, if there was a 0 somewhere else, you might want to expand on something different. So you could also expand on the second column, the third column, or whatever. If you can get one of these, if one of these values happens to be a 0, then you might want to expand on that particular row or column, right? So I'm not going to finish this, but you can imagine what would happen. You would need to find out the determinant of the 2 by 2 matrix and work that out. But I want to show you if I expanded on a different row or column, I would have something like this. So I would still need to keep track of the pluses and minuses. And as I move around the matrix, each of these things would have, I don't know what's going on here. Each of these things will have a sign. It's actually a minus. Minus, plus, minus, plus, minus, plus. Each of these things would have a sign. And if I expand on the third column, I will have a plus C. And then after I cross out the row and column that contains C, I have D, E, G, H left. And then I would go minus F. And then I would have A, B, G, H. And then plus I, A, B, D, E. Okay, so these should be equal to each other if you were to expand the 2 by 2 determinants. Okay, so we're not going to do that. Instead, what we're going to do is take a look at our 2 examples, and hopefully we can do this quickly. Our 2 examples that show that things are independent or dependent. So let's start off with this e to the x and e to the minus x. So this is just going to create a 2 by 2 matrix. I want to, so the Wronskian of these 2 functions is the determinant of e to the x, e to the minus x. Now the derivatives. Derivative of e to the x is, what is it? E to the x. And then the derivative of this is negative e to the negative x. Right? The determinant is going to be e to the x times negative e to the negative x. What's this? That's just 1, right? And then minus these things, e to the x times e to the negative x, which is also equal to 1. So we have -1 minus 1, that's equal to -2, and it's not equal to 0. So it's linearly independent. Now the other one was dependent, right? So let's see if we can remember those functions. y1 was equal to, what is it, e to the x? y2 is equal to x, and y3 was equal to, oh, we have to do a 3 by 3 matrix. So the Wronskian is e to the x, x, and 4xe minus e to the x. Now I need to take derivatives. What's the derivative? E to the x, e to the x, derivative again, e to the x. Derivative of x, 1, 0. So I might want to expand on either the second column or the third row, because there's a 0 there. And what's the derivative of this? This is 4 minus e to the x, and then negative e to the x. Okay? So this is my Wronskian matrix. Now I'm going to expand along, I want to expand on the second column, because that looks kind of easier. So I remember my pluses and minuses. So this starts off with a minus. So negative x times, and I cross out the row and column that contains that. And then I have e to the x, 4 minus e to the x, e to the x, and negative e to the x. Okay. Next one is a 1 times, I cross out that thing that has the row that contains 1 and the row and the column that contains 1. I have e to the x, for x minus e to the x, e to the x, negative e to the x. And then the next one is a negative, but it's going to be 0, so I'm not even going to care what's happening in that matrix, because that's going to disappear. What do we have now? Negative x, and then the determinant of a 2 by 2 matrix. So this is negative e to the 2x, e to the x times e to the x is e to the 2x, minus e to the x times 4 minus e to the x. Okay, that requires some attention. Plus 1 times negative e to the 2x minus e to the x, for x minus e to the x. This is negative, negative is a positive, x e to the 2x. I'm going to do a couple of multiplication steps here. Negative, negative, that's positive. 4x e to the x. Distribute. And then here I have negative, negative, negative. So that's a negative. E to the x, e to the x, and x e to the 2x. And then I have minus e to the 2x, and then distribute that, minus 4x e to the x plus e to the 2x. Oh, does that turn out to be 0? So these two go away, these two go away, and these two go away. So that's equal to 0, which means these three functions must have been linearly dependent. Okay? That's the Wronskian. So we'll get some problems to work on. A Wronskian is going to be our way to check if the functions are linearly independent. That's basically it. In general, we're going to be able to tell, so it's not going to be that big of a deal. So all right, so the definition is that if you have a list of functions that are linearly independent to an nth order differential equation, and you have to have n of these functions that are linearly independent. Remember those little functions? Well, by little, I mean these are little functions that are linearly independent. Then, if those are all linearly independent solutions to your differential equation, then that's called a fundamental set of solutions. And then here they talk about the existence of a fundamental set. There exists a fundamental set of solutions for any homogeneous linear nth order differential equation on some interval I. And so what we can do is we can string up, by string up I mean write it as a linear combination. We can write these functions as a one big linear combination of these functions, and then that's going to be your general solution. But they have to be linearly independent. You thought you can or couldn't? If they're dependent, then what we're saying is that they're essentially the same function. So in other words, if we go back to this example, if we have these three functions that are dependent, then what we're saying is that why can't we just eliminate one of them, and then now we can write the other two as a linear combination that would take the place of the other one. And so we don't need that other function. Does that answer your question? I have a feeling you have a different question in mind. Okay, hopefully, because our next piece of information is coming. And the general solution for our differential equation is going to be the linear combination of those fundamental solutions. Sounds all technical, huh? So the whole point here is to come up with a general solution for your homogeneous differential equation. And the general solution will be the linear combination of all those linearly independent functions. If we can find these linearly independent functions, all we have to do is write them as a linear combination, C1 times 1 plus C2 times second, C2 times third, etc. And then we have a general solution for our differential equation. Out. Yes. Yes. So right now, this is the underlying theory behind it, and we haven't learned how to find y1, y2 yet. But we will, and we will need to check if they're linearly independent, and then once we do, then we know what to do after that. Okay? So the general idea is find little solutions, and then we string them up to this one big solution. All right. That's the second part. Part 3. non-homogeneous equations. Sorry, this is yeah. Hopefully. No, it is. And the basic idea here is that we're going to, it's called another superposition principle. Superposition principle seems to be just, if you have a solution to something and if you have another solution to something, you just add them together. That's what it seems to happen. That's what seems to happen. And so here's what they're saying for this first part. Y sub p, that does not have any free variables or arbitrary constants. If y sub p is a solution to a non-homogeneous differential equation, and that's called a particular solution. Not only that, the general solution for your non-homogeneous differential equation would be your solution to your homogeneous differential equation plus that one particular solution that you found for your non-homogeneous differential equation. So this, from the previous theorem or statement or whatever it was, is a general solution to the homogeneous differential equation. And this is a particular solution to the non-homogeneous differential equation. And put those two together, then we have a general solution. The whole thing is a general solution of the non-homogeneous differential equation. Okay? So we have a general solution to the homogeneous differential equation. We have a particular solution to the non-homogeneous differential equation. And if you put them together, now you have the general solution for the non-homogeneous differential equation. Oh, man. All right. So, this one I didn't even bother typing because it's just in the book. I mean, they're all this stuff is in the book, and now it's in the notes that you can just download and copy. So here's more. The superposition principle says is that if your non-homogeneous part of the differential equation, the g of x, is a sum of a bunch of functions, then you can find particular solutions for each of those little functions, and then put them together to be your particular solution for the big function. Now, I can see that you guys are just saying, screw it, whatever. And then you're hearing blah, 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 blah as I'm talking. But when we start doing these problems, we'll come back and refer to these ideas and then we'll see the connections a little bit clearer. Because when we're kind of doing foundational stuff, it seems all abstract, and it is. But when we start actually doing the problems, these things will start making a lot more sense. Yeah. Yes. This is a nice summary. You have to find the solution to your non-homogeneous differential equation by finding those linearly independent functions. And if your differential equation is non-homogeneous, or if your differential equation is homogeneous, then you're done. If your differential equation is non-homogeneous, then after you find those little functions, then you have to find a particular solution for the non-homogeneous differential equation. We'll find techniques for that. And then once we do that, then we string them up together. By string them up, I mean just add them together, and then you'll have your general solution. All right? So try to look through the first section in chapter 4 and try to do a couple of problems from that section. And then when we come back, let's solve some differential equations. Yay. Woo.